often, one well-written and complex SQL query can take the place of lots and lots of little tiny SQL queries that you think do what you want them to do. In other words, a lot of times people trying to write into their application what they really ought to write in 2 lines of SQL or 1 line of SQL means a lot more work for the database. And so if you start to write really expressive SQL, you won't have as many problems with database load. Also, if you know how to write better SQL, you know how to write queries that don't load the database as much anyway. Sometimes it is useful, nonetheless, to reduce the load on the database by moving some of the logic out of SQL and into the application. I recommend that in general you avoid doing this unless you have evidence that it's necessary. That's called premature optimization if you do it the other way. Another thing, more complex queries are harder to write and debug. Another reason people don't like to use SQL so much. This is true, but so is more complex programming. More complex queries are harder for the next guy to maintain. See above, so is more complex programming. Finally, good DBAs are often more expensive than good programmers. This is also true. This is probably the most widely applicable reason not to write expressive SQL, because you really don't want to confuse the inexpensive slob that your boss hired to follow you. Next slide, please. A couple of reasons to do stuff in SQL. The database is often much more efficient than your application for messing with big chunks of data, especially if you're writing in some interpreted language. So getting a whole bunch of data from the database, dumping it into your PHP application or whatever, and then processing it in there is probably not the right way to do that. Probably doing it in the database will be faster. The database is better tested than your application. It just is. Deal with it. The database is there for processing big chunks of data, so use it for it. SQL is designed to express relations and conditions on data. Your application is not. The language your application is written in is not. So use the database rather than your application. And finally, a better understanding of SQL allows you to write queries that perform better. This is sort of a theme that I'll keep bringing up. But if anybody speak another language, or several other languages? I imagine there are lots of missionaries in the room, for instance. I speak French, and I know that when I was learning how to speak French, there were often times that I'd get close to a word and realize that I don't know the French version of that word. And so my sentence would take this little path and kind of come around here and say the same thing in a different way. And the only way that I was able to communicate freely was that I happened to know a couple sort of shortcuts and circuitous paths through the language to avoid the pitfalls, to avoid the holes in my grammar and vocabulary. If you happen to know SQL well, you can find all sorts of different ways of writing a query that does the same thing. The end result being you can choose the one that runs the fastest. If, on the other hand, you only know one way to write it, you have to deal with any side effects or any slowness that that particular one way has. Next slide, please. In short, the database is there to manage the data. Your application is for handling business logic. Write your software accordingly. Next slide. So let's get started. Next slide. These are 2 tables that we're going to be using for the next couple, the next couple of slides. Kind of pay attention to them. They're pretty easy to understand. Here we have an ID value 1 through 4, a data value A1 through A4. And here we have ID values 3 through 6, not necessarily ordered the way you'd expect, and values B3 through B6 similarly. Next slide, please. Can somebody describe to me what a join is in SQL? Just in general, what's a join? Anyone? Way back.
Grouping together of 2 tables based on common values or some calculated Boolean expression.
Okay, taking 2 tables and sticking them together somehow. I'm going to call them relations. The reason being that a table is generally a physical object on the database, a physical thing in the database. A relation is a group of data, which might either be a table in the database or some manipulation or mutation thereof. But in any case, taking 2 relations and mixing them together somehow. That's a join. There are several different kinds. Next slide. This is my attempt at the grammar of joins. Don't bother memorizing this. It's probably wrong anyway. Next slide, please. First of all, the cross join. The cross join is just what happens when you say select star from table 1, comma, table 2, or table 1 join table 2, and nothing else. The idea of a cross join is that you take every row in table 1 and you match it up with every row in table 2. So if you have 4 rows in table 1 and 5 rows in table 2, you get 20 rows that come out, right? This is called a Cartesian product. One of the difficulties of the cross joins are very useful for some things. One of the things you have to watch out for, though, is that if you have n rows in table A and m rows in table B, you get n times m rows coming out. That number can get big very quickly. And if the database has lots of rows it has to deal with, it gets slow very quickly. So watch out for these. But these are useful. Next slide, please. So for instance, if I cross join A and B, remember my 2 tables A and B? I get every value in A combined with every value in B. And that would be a total of 16 rows that I haven't shown you all here. Make sense? Okay, next slide, please. An inner join looks a lot like a cross join. But an inner join uses far fewer rows. And the reason is that now we're starting to bring in some of those conditions that the gentleman in the back talked about when he was talking about joins, that we're merging 2 tables together based on some condition. So this will look like select whatever from table 1. The most formal way of putting it, inner join table 2 on some values. What I'm saying is combine table 1 and table 2. Return only the rows where some field in table 1, in this case, equals some field in table 2. So for instance, I can join the 2 ID fields, which I'm about to do. This only returns rows that satisfy this condition, and this condition can be very complex. This doesn't have to be equals. There can be multiple clauses in there. And this is equivalent to a cross join with a where clause. Does that make sense? Okay, an example. Next slide, please. So here I'm inner joining A and B using, what's this using phrase? Anyone? Using says, is syntactic sugar. It's a way of saving keystrokes. I could say join A.id equals B.id. Instead, I just say using ID. That says A and B have a column, both have a column called ID. Match it on that column. That make sense? Okay. Remember that table A had ID values 1 through 4, and table B had ID values 3 through 6. So the only 2 overlapping or matching IDs are 3 and 4. And so those are the 2 rows that I get back in this inner join. Column that comes out of this. Any questions?
Yeah. The stuff that you're going to show, is this just plain vanilla SQL, Oracle SQL, MySQL, PostgreSQL?
This is pretty general, and I will try to, there are some places, some of the things that I'm going to talk about that are specific to some database servers. I will try to make that clear insofar as I am aware of it. I know that this works in Postgres. I can't speak for others. For instance, this using clause may be a Postgresism. I don't think so, but to be honest, I'm not sure.
If I use a string in one table and a numeric in another, does that shortcut work?
It depends on how your database works. If your database knows how to cast those automatically and is willing to do it, then it might. And you might run into problems with that if, for instance, casting between string and integer happens to be slow on 90 million rows or something like that.
In cross-join versus a inner join, you said it's the same thing as using a where clause. I know that MySQL would most likely use its optimizer to go the shortest route, basically.
Right.
You would attempt to, anyways. I'm curious on PostgreSQL, is that the case? And if not, kind of what's the back end doing in the difference between a cross-join and an inner join with a where statement?
The question, for the sake of the recording, is that I'm going to try to remember to do that from now on. Helpful recording people listening even hereafter. The question was, what happens in the back end when I see the difference between a cross join and an inner join? I can't speak generally. In the case of Postgres, it would see this inner join. It can effectively ignore this inner word. It will see that I'm joining A and B, that I'm not doing an outer join with one of the types of outer join, which we're going to talk about later and require special cases. It will see that I'm doing a join, and this using ID will get translated into on A.id equals B.id. And then that A.id equals B.id is just a qualifier. It could be put in an on clause here, or it could be put later on in the where clause. in the case of Postgres anyway, those qualifiers may very well get moved around a lot. If you have a big complex query, like if this is nested down at the bottom of some big query, those can get moved all over the place. So those might get moved all over. The place where the join happens might get moved all over. But what you end up with is effectively this is a cross join with a where clause. It's the same mechanics that will handle a cross join with a where clause versus an inner join because they're logically identical.
Yeah, just to kind of follow up with that, on Postgres, if you use explain, analyze, and then your query, it'll break it down for you and tell you how it's trying to execute and process the query. And it'll also give you hints on as far as what type of indexing, if it's even paying attention to your indexes. And then you can kind of go from there. That's usually what, if you collaborate with anybody else online, they'll want to see the explain, analyze so that they get an idea how your database is running underneath. And that they can follow up with follow-up questions of like, why are you doing it this way, or have you thought about this? It just kind of opens it up to tell you how it wants to do it.
Next slide, please. Okay, can somebody tell me what an outer join is? An outer join, these inner joins only return rows that match this condition that I've come up with. In the case of an outer join, I might return all of the rows from one or the other or both of the relations that I'm joining. And in cases where, for instance, I'm joining A and B, doing an outer join of A and B, in cases where there is no row in B to match a row in A, I will instead return nulls for B. Does that make sense? So I'm going to return all of the rows from one or the other of the two relations that I'm joining, and I will return nulls where the other relation doesn't match. So there are three types of these: left, right, and full. And whenever you write left join or right join or full join, you don't need to include the outer because it's just implicit, it's understood. In the case of a left join, I have A on the left and B on the right. I will return all of the rows from A, all of the rows from B that match something in A, and nulls everywhere else. Or in the case of a right join, it's swapped. I'll return all the rows from B, all the rows from A that match something, and nulls for A everywhere else. And finally, in a full join, I will return all of the rows from both sides of the query, inserting nulls wherever they're needed. Does that kind of make sense?
Is the left and right just determined on how you read the from?
Exactly, just how you write it in the query. And then the planner may very well swap those around for whatever that means within the internal representation planner. This will require an on clause or a using clause because you have to give some condition to this join so that it knows what it's joining on. In general, you probably can't squish those into the where clause. I know in Postgres you can. Anyway, next slide, please. We'll see an example. Here I'm joining A and B with a left join, so you'll see that it returns all of the rows of A with some nulls where there was no row for B to match. Simple enough? Next slide. Similarly, right join, I have null rows in this column from A. I should have done this better. This is the ID column, this is the column from A, this is the column from B, even though they're both labeled value. But you can tell this because of the data in there. It's conveniently labeled for what table it came from. So there are nulls in the A column, where there was no match to what was in B. Finally, one more slide, please. Finally, a full join. I've got all the rows from A, I've got all the rows from B, and I've got some nulls on both sides. Okay, next slide, please. Let's see. Oh, here we're finding all the rows in A with no match in B. This is the only difference here is that I've added this where clause where B.value is null. Does that make sense? So anything that doesn't have a match in A, I've returned the ID of all of the rows in A that have no match in B. Clear enough? Next slide. Okay, natural is another syntactic sugar thing that may or may not show up in your database. Natural says, look at relation A and relation B, look at their column names, and any column names that match, join together on those columns. In this case, our table A and table B both have an ID column and a value column. So if I were to natural join them, it will join on both of those columns. This can be really useful if you have your person table and your address table and they both have a person ID or whatever. Then you can just say natural join and it will join on person ID. Some may consider this bad programming technique, kind of like some people say select star is bad programming technique. I'm carefully avoiding any side of those arguments, though I have well thought out and staked positions. But anyway, so that's natural join. Next slide, please. Here we've joined A and B on ID and value. Think about this result in your off hours if you feel like it. This looked for rows that matched both the ID and the value columns. Note that I did a full join, so it's going to return every row from both relations. It found no rows that matched, right? Because none of the values in A identically match values in B, in the ID and the value column. But it's a full join, so it returned all the rows from both. So we've got 8 rows. Next slide, please. Self-joins are particularly counterintuitive, where I take table A and relation A and join it to itself. But these are very useful. Next slide, please. For instance, I have an employee table which contains employee's first and last name and the employee's manager, some value that represents the employee's manager. So if I want to get a list of, let's see, first, oh, here we go. Okay, so the manager column, let me back up a little bit. Picture this table. I have an employee table. I've got an ID, I've got a first name, I've got a last name, and I've got a column that references itself that is the ID of the person's manager. Okay, my name's Josh. My manager until a couple days ago was Greg. So I have an entry in here. Greg has an entry here. Under my manager column, then Greg's ID shows up. Okay? I want to get a list of my name and my manager's name, or everybody's name and everybody's manager's name. I could do this way. This is a subquery within parentheses here. What this is going to do, this looks like it's missing a from clause as well. So anyway, badly written, but you kind of get the idea. I thought I tested all of these. Anyway, this will get my first name, my last name, and then have a subquery to select the first and last name for the person whose ID is my manager ID. And note that I'm using these little table aliases to kind of disambiguate things in my badly written query. Here's a faster way of doing it. The reason this is faster is that in this version, most likely what will happen is I will find one row in the table and I will execute a subquery for it. I will go to the next row in the table and execute another subquery. So if I have n rows in my table, I'll execute n subqueries. And that gets to be a lot of subqueries. The faster way of doing it is a join. I will join my employee table with itself. So I'm selecting e.first. This is concatenation space, concatenated e.last. So my first and last name with a space in them. And m.first joined with m.last. E is the employee table, and m is the employee table. E.manager equals m.id. Does this make sense? Okay. What this will return then is my name and my manager's name. Next slide, please. I may even have an example. Nope. Okay, more useful stuff, except the guy in the back first.
I work on a database that has as many as 80 million to 100 million rows in one table.
Okay.
And I've found a lot of queries that programmers before me wrote that have subqueries in the where and select clauses. And so far, every situation I've been able to find a much faster solution by doing inner joins. Have you ever seen a situation where a subquery and select or where clause were required?
I'm sure there are some. I frequently join subqueries together, and that may just be my style thing, and that doesn't have the same performance limitations. The sort of thing that we're both talking about, that I was talking about in the slow version of the employee query, is what's called a correlated subquery. The idea is that you have some subquery that you run once for every single row of the input. And that's where things start to get really slow. And that's kind of a pattern that you get used to avoiding when you know what it is and start paying attention to such things. A couple of useful operators that some databases have. Next slide, please. Subqueries. I think we're kind of, you're familiar with subqueries. You know what a subquery is. You wrap parentheses around some other query, and suddenly you've got something that you can treat like a table. So anyway, a couple of subqueries. I'm not even going to read through all of these. Download the slides and look at them if you want. You know what subqueries are. Next slide, please. Set operations. I don't know if your favorite database has these. Most do, and most people never use them, sometimes with very good reason. Intersect. You know, think of your Venn diagrams. You've got two circles, and where they overlap. The intersection is where they overlap. That's what intersect does. And it gives you all of the values. You give it two queries, and it gives you all of the values that are in both. Kind of like a join. Union appends one set of rows to another set. So I select everything from this table, union everything from this table. qualification there is that the data signature, the columns and types returned by both queries have to be identical. This can be really useful. I used this the other day, in fact. Except, so again, think of your Venn diagrams and your set operations. Returns the rows in one select that aren't in the other. So select A from table 1, except select B from table 2. Again, you just pass this 2 sets of rows, 2 queries, and it will return you the set from one that aren't in the other. Make sense? Next slide, please. I really appreciate that, by the way. That's a lot of help. Familiar with the coalesce function? This comes in various names. Oracle calls it NBL. This is kind of like an if. If A is null, then return B. Otherwise, return A. I don't go into nulls and 3-value logic in this presentation, but suffice to say it can get kind of strange when values can be true, false, or null. So often you'll find that your queries are really misbehaving, and it's because there's a weird null value in there that you're not expecting. Coalesce helps you get rid of those. Familiar with case operations? This is like switch case or select case or whatever variant your language of choice has. But you can say case when some condition is true, then do something else, do something else. I'm missing an end in there somewhere. But in any case, this lets you do more complex conditional logic within your queries. Okay? Next slide, please. Series generation is useful. This one definitely will vary from database to database. The Postgres version is called generate series. And this just returns a set of numbers. You can use this like a for loop. When somebody said you can use this like a for loop to me for the first time, my very first thought was, why would I want to use a for loop in a database? We'll see one example of why you want to later on. But in the meantime, select star from generate series, 1,5 gives me values 1 through 5. So keep that in the back of your head. Next slide, please. Common table expressions. Here we get kind of fun. This is some of the more advanced stuff. Anybody know what a common table expression is right off? A common table expression is, first of all, you MySQL folks are left out in the cold on this one. Sorry, switch databases. Also, anybody in Postgres before 8.4 upgrade, please. A common table expression is kind of like defining a one-time view for your query. And you're looking at me like, why would I ever want to do that? There are a couple of reasons. If you've ever written a particularly large query, you'll find that one of the things you do is you write little chunks of code and you squish them all together. Right? Anybody? Does anybody else do that? Come on. Okay, there's not. There's a couple hands. Good. I feel validated. So one of the reasons you might want to do this is that you can then define a whole bunch of chunks of code at the top of your query with meaningful names, and then all of the weird logic that has to glue them together can just refer to those names, rather than having to actually embed the big ugly chunk of code. So it makes your code prettier. There are other neat things you can do with them, because common table expressions allow recursion. And you're thinking, okay, why do I want recursion? Anybody use recursive queries? Oracle has this thing called connect by. I'm sure MS SQL has something like it. Recursion within a common table expression, a CTE, is generally speaking going to be much faster than doing it in your application. For instance, think of this same manager-employee hierarchy. This is kind of the classic example. But the manager-employee hierarchy. So I'm Josh, my manager's Greg, Greg's manager is, I don't know, John, who's Greg's manager? Greg's manager is here, and so we have this whole list of managers all the way up this organization, and I want to traverse that. Sorry, video people, I'll quit moving around so much. I want to traverse that list, and I want to find, for instance, all of the people who Greg manages and all of the people that they manage. Are you starting to see the recursion in here? This is where this stuff gets really useful. If you're doing this in Python or Lua, since nobody uses Lua, I can pick on Lua. Does anybody use Lua? My window manager does.
MySQL.
Does it really? There is a PL Lua, so you can use Lua in the back end of Postgres if you want. So I'm in my code, and I select Greg, for instance, and I get Greg's ID. And then I select all of the people whose manager ID is Greg's ID. So there's the list of people that Greg manages. Now I loop through them in turn. and with each of their IDs and get all the people that they manage. And then I have this list, and I keep executing all of these queries over and over again. Now, the problem with that is you might prepare your query so you don't have to deal with parsing this every time, but you keep having to go back and forth to the database. And the database has to keep going back and forth to the disk to get all of this. It would be really cool if you could just tell the database to do this once, load all of this stuff into memory, and the database gives you one result set that contains everybody, right? Same couple of nods. Thank you. That's okay. So here's where recursion and recursive CTEs get really cool. Next slide, please. Okay, what am I doing here? Yeah, okay, a simple example. I'm trying to remember why I did this example. It's probably too simple at this point. Okay, so in any case, I've got two relations. I'm building them artificially with generate series, so I have values 1 through 3 cross-joined with values 8 through 9. Does this result make sense? Okay. Now all of a sudden picture that this second relation were some really big, hairy, ugly query. Can we do that? Okay, next slide, please. So here's how I might handle it with a CTE. With T as, and then I define my query, my generate series 8 through 9 query. So I'm calling T this chunk of SQL code. So then all I have to do is join my generate series 1 through 3 with T. Simple enough? Now once again, if you picture that T were instead some really big, massive, hairy query, you can start to see where this makes things look much cleaner, right? And I get the same result. Next slide, please. Okay, the last example was cheesy. And
How is that different than creating than having a view?
Well, first of all, with a view, you're not going to be doing recursive stuff. You could define a view and tell the database, create this view as select generate series. You could do that. And then you have this view, and then maybe you drop it when you're done. That's a fair bit of overhead for having to deal with all of this. The major draw for something like a CTE is not so much that you can clean up your SQL as that you can do some of this neat recursive stuff. I'm sort of introducing the syntax here, but the really cool stuff is that you can get recursive with them. Next slide, please. Okay, so here's my employee and my manager table. John Doe is apparently the head honcho because he has no manager. Fred Rogers, ID number 2, is managed by John Doe, as is Speedy Gonzalez and Carly Fiorina. Anyway, you can kind of see how this table works, right? Next slide, please. Okay, here's where I'm getting my management hierarchy. And this is kind of a fun query. First of all, ignore the entire with clause, which starts there and comes down here. Ignore that. What I'm selecting is the employee ID, the first and last name, and this thing called manager names, which presumably comes from up here somewhere. We'll look at that in a second. From my employee table, joined with T. I tend to call this T. You can call it whatever you want. It doesn't have to be T. So joined with this thing called T, where employee ID equals T.ID, whatever T.ID is. Make sense so far? Let's look at this recursive clause. When you start to do recursive CTEs, you're going to see this pattern a lot. You will see one query, union all, some other query. Do you remember union? Tack the results of one query onto the end of another. What's union all? Anyone? John?
Doesn't remove duplicates. Normal union removes duplicates so that it's because it's using set logic. Union all kind of violates that and just tacks union.
Right. So union all is really what you want if you're just tacking queries on the end of each other. Union will remove duplicates from that result. That tends to be a fairly common gotcha to introductory users of union, so pay attention to that one. So in general, you have what you have is a start case and an end case, if that makes sense. You have some start condition union with some other condition. In this case, my start condition, I want to start with John Doe. Remember, he's the guy at the top of the hierarchy. Manager is null. So I'm going to select his ID, his first and last name, I'm going to call his first and last name manager names. You're familiar with this as syntax to rename columns. I will select his ID, his first and last name. I will call that result manager names from the table E, where manager is null. This part of the query is just going to give me John Doe and his ID, correct? Okay. Some other table that might give you something else, but for our example, that's what it's giving me. I'm going to union this with a whole bunch of other stuff. I select first and last name, comma, oh right. Can we go one more slide just to see, here's the result that I'm aiming for. This is recursive, so I'm going to stack all of these recursive results together, and I have to present that somehow in the result set. In this case, what I've given you is each employee's name plus their manager name, comma, their manager name, all the way up the hierarchy. Make sense? So John Doe is at the end of every one of these strings. Okay? Okay, did we work out how to go back a slide? Sweet, can we go back a slide? Thanks. All right, so all that being the case, I am going to add, up here I selected the user's ID and a first and last name that I called manager names. In this part of the query, I'm going to modify manager names, and I'm going to tack my own name onto the beginning of it. Make sense? So that if here I just select John Doe and his ID, and then as I recurse through and I'm some other manager, I'm going to prepend my name to John Doe and whatever else happens to be in that list with a comma and then whatever value was already there for manager names. So here I select my ID, my first and last name with a comma and space, and whatever is already in the manager names value. Also from my employee table E. And here's where it starts to get weird. I'm joining this to T. This is where the recursion comes in. Remember, T is this thing that I'm defining right here. So I'm joining it with myself recursively, where you recognize this condition where E.manager equals T.id, and where manager is not null. This is kind of a key criterion here to make sure that John Doe, who came in this part of the query, is not also included in this part of the query. Does that make sense? Kind of. This is the sort of thing that it helps to sit down in front of a compliant database and play with for a while. So if this is not immediately clear, please don't consider yourself terribly dull.
Is the union an actual important part of this as far as the database is concerned, or is that totally irrelevant to how you're getting the data you want?
To make the recursion work, you generally give it a start condition and you union all of that with some ongoing recursive condition. So this, and note that this stop condition, this recursion here will stop because at some point you hit the bottom of the hierarchy and then there's nobody where, I am John Q. Schlub and my manager, I am nobody's manager. And so that's where the bit of the recursion is going to end. But in answer to your question, in general, you have a start condition and you union that with some ongoing recursive condition that will eventually, hopefully, end. Does that make sense? So in other words, the union all is pretty common when you're doing recursive stuff.
Is it possible to do it without the union all? I mean, is that how the database knows that's the start condition? Is it's the thing before the union?
The question is it possible to do it without the union all? That's a good question. I don't know. I'm not sure. Next slide, please. So you can see the result that this gives. Note also that because of the way we wrote the query, everybody shows up in their own manager names list. We could prevent that with a bit more query logic, but I figure we've kind of bitten off enough with this one. So we have Martha Stewart. Martha Stewart is managed by Speedy Gonzalez, who's managed by John Doe. Make sense? And note that there are 4 names in here, 3 names in here, 2 names here, 1 name there. So this really is a recursive thing, and it's recursing exactly as much as it needs to for every person in the employee list. Okay? Next slide, please. Of course, when you are a math geek, the very first thing that you do when you can recurse is you draw fractals. So here's a SQL query. This is Spec Compliant, and its result is the next slide, please. Anybody familiar with this? So family dot sets in SQL. I cannot claim, unfortunately, responsibility for this result. This showed up on a Postgres mailing list and got a fair bit of totally deserved attention, I think. Anyway, Mandelbrot sets in SQL, that takes a little bit to run. It's not, terribly bad. But anyway, that's, your laptop will chew on it for a little while. That query is spec compliant so far as anybody that I know of has been able to discover. It looks exactly like it should. It probably uses generate series in there, which again I think is a Postgresism, but pretty much every database has something like that. So fractals in SQL. Next slide, please. Window functions. A window function is kind of a neat thing, and I had a rough time when Postgres was first taking on window functions. By the way, this is another one where you MySQL people are kind of out in the cold, so enjoy your party, I guess. These were a tough one for me to understand. Do you know what an aggregate function is? An aggregate function takes multiple input rows and returns one output row. A common example is count, like when you select count star from whatever to see how many rows are in the table. That count function is an aggregate function. It takes all of the rows in the table and it returns a single value. So you have things like count, sum, mean, median, standard deviation, whatever. All of those are aggregates. A window function is like an aggregate that returns a set of results, and it may be a different set of results for each input tuple. A tuple is a row, kind of the database slang for a row. So for each input row, it may return a full set of results, and then that set may change from row to row. Does that make sense? That's probably an inaccurate description, so don't sit on that one for too long. If you're really keen on using some window functions, get yourself a database that does it and play for a while. Because this, like CTEs, is one that really takes some experimentation to get used to. But this is how you do things like ranking, moving averages, and again, it's like a set returning aggregate function. Next slide, please. Okay, so here's our employee table, and we're going to throw in salary and department information. This is another kind of classic window function example data set. So we have salary information for everybody, and we have the department that they're in. Next slide, please. Okay, I want to rank, first of all, if I wanted to rank the entire company by salary, who makes the most, who makes the least, and order them in the middle, that's easy, right? We'd select star from here, order by salary, descending. Okay? I want to rank them by department. So I get all of the salespeople ordered by their own salary, all of the administration by their salary. Okay, there are ways that you could probably do this with fun order bys. Here's the way you do it with a window query, with a windowing function. This rank is the windowing function. And when you use a window function, you pass it the window that you're using. So I'm selecting first, last, salary, and department. Ranking by, let's see, I'm partitioning by department. So I'm going to divide my entire data set up by each department, and I'm going to order each of those partitions by salary in descending order, and I'm going to rank those. Kind of make sense?
Are these only available in Postgres?
Postgres, Oracle has them. I imagine MS SQL does. This is a standard thing. Both CTEs and windowing functions are part of the SQL standard, so that this isn't just for you lucky few who use Postgres. This is a common thing. Next slide. Okay, what I get? I've got each of the departments, and I've got each department ordered by salary. And here's the bit that you can't do with your order by. Each of these is numbered. So I could, for instance, select all of these whose rank is 1, and I know that they're the highest paid person in their department. Make sense? Okay, next slide, please. Suffice to say, before I move on too far, there are other windowing functions. There are things like rank versus dense rank that will let you handle ties, and the whole list of windowing functions has just escaped me, so I can't give more examples. Anyway, find your favorite database that supports them and look in its documentation. A couple of real-life queries. Next slide, please. Okay, here's something fairly simple. This is from a thing called Ricardo. Ricardo is a Postgres replication system. Anybody who's dealt with Postgres replication knows that there are many such systems. This is one of them. I happen to like it quite a bit. And this is the slow and the fast version. I told you at the beginning of this that one of the reasons for knowing decent SQL is that you can speed your queries up. You can find other ways to say in SQL the same thing and get a faster query as a result. So here's one example. We have this table. Ricardo has this table called Ricardo_rate. It tracks every time a group of tuples, a group of rows, is replicated from one place to another. It tracks how many rows were replicated, how long it took to replicate them, a few other useful things, including what sync that was. In Ricardo, you set up multiple syncs, where you say, these tables are part of this sync, and as part of this sync should be moved over to these tables on this server somewhere. So the whole idea of this replication system is I can make changes in database A, and my changes show up in database B, which may be on some other totally different server, hosted in Algiristan, and it just handles the replication for me. And so I have these syncs saying sync table A to table B over here, and my Ricardo rate table keeps track of all of those. So in a typical installation, I may have 8 or 10 syncs, and these syncs run every couple of seconds. For a normally updated database that gets some amount of use, I will have jobs running as part of each sync every couple of seconds. So this Ricardo rate table can get pretty big. Before I go too much farther, this is the fast version. There's another table called sync that has a list of just all of my syncs. So again, there may be 8 or 10 rows in this, or 20 if you've got lots, or 1 if you haven't. And I am, well, we'll talk about that in just a little bit. Next slide, please. Okay, so the Ricardo rate table can get huge, right? Because I'm doing one job per sync every couple seconds maybe, or multiple jobs per sync every couple of seconds. So did you notice the first query finds distinct sync? What does distinct do? Gets rid of duplicates. Can we go back one slide? This first query says find distinct sync from the Ricardo rate table. So remember, the Ricardo rate table is millions of rows. And if I have to go through and find just the syncs that are in that table, that's going to be several million rows of processing that I've got to do, right? Okay, so that's slow. Next slide again, please. So the sync table contains a list of all possible values in the Ricardo rate sync column, right? And it contains only one instance of it. So I have the Ricardo rate table that has 80 million rows, and one of 8 or 10 values distributed in its sync column, or I have the sync table that has 8 or 10 rows total. So back one slide again, please. Thanks. Doing a great job. So in this table, in the fast version of this query, I am joining, I am selecting each sync from the sync table where there exists at least one row in Ricardo rate using that sync. Does that make sense? You're familiar with this exists clause? Exists will return true if the select statement that you pass it returns at least one row. So I'm getting all of this, in each version, I'm getting all of the syncs that exist in the Ricardo rate table. In this version, I'm doing it by going through 80 million rows and looking for duplicates. In this version, I'm doing it by grabbing each of 10 rows, of 8 or 10 rows, and scanning through this table only far enough to see if it's ever mentioned, if that sync is ever mentioned. Does that make sense? This ends up being a whole lot faster. 2 slides, please. Okay, even 3 slides. Okay, this is a big, huge query. I'm getting little 5-minute time signals and things, so I'm not going to be able to run through this in great detail, but this is a good example of breaking stuff up into parts. This is more Ricardo stuff. This Ricardo rate table, we also wanted to draw graphs of how much time was spent replicating in each, say, 5-minute bucket over, for instance, a 24-hour period. So we wanted a SQL query that returned each of those 5-minute buckets over this 24-hour period, and the total time or the average time or something spent synchronizing in each bucket. Okay? Next slide. This, I just explained all of that. Next slide. Okay, this query is made up of a whole bunch of parts all joined together. Okay, so effectively what I'm doing, I'm going to start at the beginning with generate series. Remember where I was saying, why would you want to use a for loop in SQL? Here's why. We wanted to create 5-minute buckets for a 24-hour day. That's 24 times 5 divided by 60 divided by, anyway, some number. I'm just creating 15 of them here. So I create values 1 through 15 with generate series. And I can convert them all to timestamps with a bunch of this logic that you can look at by downloading the slides, because I'm not going to go into it. Next slide, please. I've generated numbers 1 through 15, and I've turned them into timestamps. And each of those timestamps is a given value separated from the previous timestamp. Okay? Next slide, please. Oh, can you go back one, actually? My SQL people, sorry, forward one more. My SQL people look at this and say, oh my gosh, decimal timestamps? So like, part of a second? Yes, there are databases that do this. This is a helpful thing. I was really surprised. I have given this presentation once before in a similar form anyway, and I got all of these, why decimal timestamp? It was really funny. I laughed. Okay, next slide. From now on, I'm going to call that piece of query the bucket query, the query that creates 15 buckets, because 15 is the number that we told it to create. 15 buckets. I need to make those buckets end at decent times. You'll notice that they ended at really weird times. I want them to start at like 0 seconds or 0 minutes, and then end at 5 minutes, and then start at 5 minutes and go to 10 minutes. This logic does that, some modular arithmetic and some other stuff. And again, download the slides and look at it. But you'll note that I'm doing things in parts. I create all my buckets here. I kind of modify my buckets in this surrounding query, and presumably in the next slide or two, go ahead one more. Then we'll start to see other surrounding pieces. Next slide, please. Okay, so these are a little bit cleaned up. I start almost at 0, actually 59, 59, and go almost to 0. Next slide. Okay, some other subquery. I am now getting all of the rate information from my Ricardo rate table. And I'm not going to go through all of this, but I'm getting the transaction commit time. I'm getting the total of rows committed, I believe, the time that it took to do this synchronization. I'm getting all of this from the Ricardo rate table. Next slide, please. And next slide, that's some of my results. I'm going to join these two queries. Here's the query where I get everything from Ricardo rate. Here's the query where I create all of my buckets. This is a right join, meaning I'm going to return every one of my buckets, whether or not there was a replication event that happened in that bucket. So that way I get every value in my 24-hour period and can easily feed into Google's charting API all of the buckets that it happens to want. I'm going to mess with some of the values that I get as a result and sum them and round them and average them to make things look pretty and sort things a little bit. And next slide, please. The end result is that I get all of these buckets. These are 10-minute buckets. But you'll see that I get the average amount of time and the total number of replicated rows, including for buckets where nothing happened as a result of my big, huge query. One more slide, please. That query again, next slide. So you end up with a big, huge query like this. But it does exactly what you need it to do. It does it efficiently, and it does it correctly. And you get there by dividing your job up into little tiny chunks. You remember learning programming when they tell you to write subroutines or modules or functions or whatever it is that your language of choice calls them? This is exactly the same thing in SQL. You write little chunks of code, and then you call those little chunks of code where needed, and you end up with a big complex query that gets everything done for you. One more slide, please. So understand your join types and use them. Know the functions like coalesce and set operations your database provides. Build your large queries piece by piece. Next slide. I think that's it. That is it. Yay. Questions, anyone? Sweet, I put you on the slide. Oh, question.
Generate series. It looked like it was essentially the same as building a simple little table and putting 15 values in it. Is that basically what it is?
Yeah, it's a set returning function. So you put it in the part of the query where the planner would expect to see, or the parser would expect to see a table. And it behaves just like a table because that's what it returns. Oh, sweet. At first SQL. So I have to figure out how to end this up. I mean, we could, like, you know, I'd get murdered. Okay, so here's a fun question. I'm trying to recall. Okay, MySQL has a mascot. This is not the question, but what is that mascot? A dolphin. What is the dolphin's name? I saw a hand in the back.
It's squeak.
Close. Anyone?
Squeal.
Squeal is close. It would be a Postgres guy that answers the question.
I don't want the book, though.
Yeah, he doesn't want to see. Okay, now you come up with a way to give it away.
I'll take it. How fast can the dolphin swim?
How fast can a European or a... Anyway. We'll take it. That was very nice. I appreciate your time. Thanks very much.